Okay, so I work in the field of recommendation systems and search, and every now and then I like to pop my head up to try to see what's going on. I think the recent trend for the past 1 or 2 years has been the interaction between recommendation systems and search and LLMs.
Let's say
You know,
RecSys.
RecSys and LLMs, RecSys and search and LLMs, and I think in early 2023, we would see some papers where people will use decoder-only models to try to predict IDs. Those didn't work very well. But at the end of last year and early this year, we're starting to see signs of life whereby some of these actually are A/B tested and have very good empirical results. So I want to highlight a few of those patterns, and we can see how it goes. The one thing that for the longest time, what we're trying to do for RecSys and search is to move away solely from item IDs. You can imagine if Eugene interacts with item ID 1, 10, 25, his next predicted interaction is probably item ID number 33. But all this is reliant solely on item IDs, and you can imagine every time that you have a new item ID, you have to learn a new embedding for it, and that leads to a closed-up problem. So I know this was not part of my recommended reads in my write-up. I will actually go back and update it to be recommended reads, but I want to discuss two papers here that try to address this. The first one is Semantic IDs, which is from YouTube. You can imagine YouTube has a lot of new videos uploaded all the time. They can't learn new item IDs for them all the time, right? So what they do is they have a transformer encoder. It generates dense content embeddings. This is actually just a video encoder that converts a video into dense content embeddings. And then they compress this into what they call semantic ID. It's via an autoencoder. So the dense video encoding is 248 dimension. But what they do is they take the encoder, find the nearest neighbors, assign that to the code book is also 248, assign it to the nearest code book, take the residual, find the next nearest neighbors, assign it. So it just keeps compressing and compressing it. In the image here, they have 4 layers. So essentially you can compress an item ID into 4 integers. In the paper, actually they compress an item ID into 8 integers. So I thought this was pretty cool. And then now that you have an item ID, you have a content embeddings, you convert it to 8 integers. How do you then learn it, right? They tried using n-gram and sentence piece. N-gram is really just, like fast text, like character n-grams. Every subword, every 1 character, 2 character, 3 characters are learnable embeddings. And then they also tried using sentence piece. Essentially, sentence piece is really just looking at all the distribution of all these item IDs. What are the most common subwords, most common subcharacters. So therefore, it's no longer just a unigram, bigram, and trigram. It's that you can learn variable length subwords. What are results from this? Well, not surprisingly, dense content embeddings itself do worse than item IDs, right? And you can see this, right? You can see this on the chart on the left here, right? You can see unigram and bigram, the red line and the purple line, the unigram, it actually is worse than the random hash ID, the orange line, for some extent. Actually, no, I didn't include the. Okay, I have the content embeddings line itself on my write-up. I didn't include it here, but this chart here is actually trying to show that they use the dense content embeddings, it's crap, but when they use both n-gram and sentence piece, it did better. So you have to do this trick whereby you have to convert that content embedding, the full dense content embedding, into its own semantic ID, and then learn those IDs. Now the benefit of this, you might be saying, hey, isn't this all back to IDs again? Well, not necessarily, because now given a piece of content, you can convert it to embedding, and then you can assign it to its nearest ID, and therefore you don't need to learn on behavioral data. So that's the benefit here. Similarly, Kuaishou, which is like a TikTok the number two TikTok in China, they adopted the same approach. They use multimodal content embeddings. So they use embeddings from ResNet, SentenceBird, and VGG to get the respective modality. And then this is just simply concatenated on a single vector. Then they take all these embeddings, they just do k-means to identify 1,000 of the most common clusters, right? Then now, therefore, each embedding is now a trainable item ID. These cluster IDs are then embedded via modal encoder. So this modal encoder, there's quite a bit to it. Let me try to simplify it. You can see on the top, it says non-trainable visual embeddings. In this example, they only use visual embedding as an example, but you can imagine all the non-trainable embeddings, They take it and they project it into a different space via the mapping network. Secondly, for every cluster ID, they convert it into learn embeddings for visual, texture, and acoustic. These are not the original embeddings that come from it. These are just the representation of the multimodal cluster ID. And then Fusion is really just concatenating it. So now you might be thinking, okay, how is this model encoder learned? How is this model encoder trained, right? This model encoder is not trained itself. This model encoder is trained within the overall ranking network, which you can see the model encoder is all at the bottom, right? So therefore, this model encoder network, it takes the user tower, which is on the left, and the item tower that's on the right, and it tries to predict the likelihood that user will click or like. Therefore, based on this, they just backprop. You backprop the likelihood of clicking or liking or following, and you backprop it through the model encoder. And that's how the model encoder learns the mapping network and the cluster IDs. So the benefit of this is that they share that outperform several multimodal baselines. I won't go through them here. And when they did A/B testing, I think those are pretty freaking significant numbers. Anything more than 1% is pretty strong in a platform like this. And the benefit of this is that they mentioned that they had increased cold start velocity and cold start coverage. It means that cold start is able to pick up faster. If it's a good cold start video, it's able to pick up faster, and they are also able to show more cold start, 3.6% more cold start content, which increases coverage. So they also did ablation studies.
Let me butt into for those new to the RecSys world. You said anything more than 1% is a big deal.
Pretty huge.
Can you contextualize like how much is that worth, or is that like
so you can imagine, right? Imagine you are making, I don't know, let's just make something up, $1 billion worth of ads,
yeah,
right? And if people are engaging more, spending 1% more time, you can show 1% more ads. That's like 10
yeah,
million,
$1 million.
right?
Okay.
So you just expand that, right? Of course, clicks and likes and follows. These are engagement proxy metrics.
Okay, so like, and is this absolute or relative? So for example, are we saying that, let's say likes was +3 right here? Are we saying they went from 6 to 9%, or are we saying they're currently 6% and now we are 6.09%?
I
Because
suspect it's relative. I suspect it's like maybe from 5% to 5.15%.
yeah,
Going
right.
from 6% to 9% is, you
Impossible.
wouldn't have to work. Yeah.
Okay. Okay. All
Yeah.
right.
So no surprises here. Using multimodality consistently outperforms single modal features. But there was also a trick here whereby they had to learn user-specific modal interests. And if you look at it on the left tower there, close to the top, there's this thing called multimodal interest intensity learning. Essentially, what they're learning there is for each user, which modality they're interested in. And then they actually map to that. For some people, like Swix is very acoustically inclined, he might care more about the soundtrack. For other people, they might care more about the visuals or the video itself. Or the text, having a good caption is worth 1,000 words, maybe. So yeah. So that's one trend I've seen, which is increasingly including more content into the model itself. The other trend that I've seen is that for LLMs for synthetic data. And there's two papers that I really like here because they just go so, they share a lot of details. And they share a lot about the pitfalls that they faced. So the first one is, this is paper I really like. It's called Expected Bad Match. It's from Indeed. Essentially, you can imagine you're providing people with job recommendations, right? And then you want to have a final filter at the end to filter out bad job recommendations. So this paper, it's not easy to get the full access to this paper online. I've included it in our, in our Discord channel, we have a thread. I've actually dropped the PDF in there. And they talk through the entire, I think they talk through the entire process, and I think it's quite a role model process. They started with looking at 250 job matches, right? 250 job matches, and then they compared it across various experts. They had very rigorous criteria, and in the end, they built a final eval set of 147 matches that were very high confident. Multiple experts agreed, and then that was nothing subjective. And then they tried prompting the LLMs with recruitment guidelines, right, to classify job match quality. And of course, they tried things like the cheap stuff, and then tried things like the expensive stuff. Unfortunately, the cheap stuff doesn't work. Only GPT-4 worked. But GPT-4 was so slow. GPT-4 took an average of 21 seconds, right? Okay, no problem. OpenAI lets you fine-tune GPT 3.5. So what they did was then they fine-tuned GPT 3.5. And GPT 3.5, you can see, let's just focus on the green boxes and then the red boxes. You can see GPT 3.5 is able to achieve as good, almost close, good precision and recall as GPT-4, fine-tuned, right? And fine-tuned from the labels of GPT-4. But GPT 3.5 was like reduced latency by 2/3 and cost by 2/3, which is perfect, right? But the thing is, you see that the average latency there is like 6 seconds, and that's still not good enough for when they needed to do it online. So then what they did is they fine-tuned a lightweight classifier. Unfortunately, they didn't go into very many details of what this lightweight classifier is. I suspect that this lightweight classifier is maybe not a language model. I suspect that it is a probably a decision tree, because they talk a lot about categorical features. And then the labels are just solely the ALM generated labels, right? So you can see their entire journey. First we build eval set, then we test GPT-4. GPT-4 good but too slow. Then we try GPT 3.5, like step-by-step incremental progress, but still too slow, so expensive. Okay, we would really not like to have to train our own classifier and have to maintain the ops of retraining it, but we don't have a choice. This is what we need to do to reduce inference latency. So that's what they did. They were able to achieve area under the curve, ROC, of 0.86. That's pretty freaking good against LLM labels. And this is, according to them, low latency. I don't know how low latency is, and suitable for real-time filtering. The benefits of this are pretty tremendous, right? You can read the benefits there yourself. But I think the one big benefit is they lowered unsubscribe rates by 5%. That is huge. For someone, if you maintain some kind of push notification or email notification thing, unsubscription rates is like your biggest guardrail. Because if people unsubscribe, you're never ever gonna reach out to them again. You would lose them. So all your customer acquisition cost is really down the drain. Like maybe you have an offer and you let people sign up. Hey, would you like to hear more about us? Okay, we give that out. But when they unsubscribe, you lose them. And so over here on the top line, in table 2, they share the invite to apply email. That's one, and then that's the results I highlighted here. And in the bottom, you can also see they had online experiments for the homepage recommendation feed. And that's how low latency this classifier has to be. It has to be on the homepage recommendations. And similarly, we see very good results, right? You can see, for example, impressions, right? Impressions drop 5.1% at threshold of 15, and then drop by 7.95% at threshold of 25. What does that mean? That means you freed up 5 to 8% of impressions. You can now show more good stuff, right? That's huge. But freeing up 1/12 of impressions is a very big deal. Freeing up more space, and as we know, more real estate is better. So I think that this was quite an outstanding result. The other one I want to share, and then we'll pause for questions, short questions before I go into 2 other sections, is query understanding at Yelp. So query understanding at Yelp was very nice. It's purely using OpenAI GPT. They had 2 things. One is query segmentation, and another one is highlights. The query segmentation one is not so straightforward to understand, but essentially, given a query like Epcot restaurants, they can split this into different things like topic, location, name, question, etc. And then by having better segmentation, they can have greater confidence in rewriting those parts of the query to help them search better. So the second bullet point gives you an example, right? If we know that the user's location is approximately there, and the user said Epcot restaurants, we can rewrite the user's location from Orlando, Florida to Epcot for the search backend. And because the search backend is based on location, by rewriting Orlando, Florida to Epcot, they were able to get more precise results for the user. So that's one example. The other example is segmentation. And the original write-up, they have a lot of good images. I didn't include those images here because I didn't have time. I only started reading this slides like an hour before. One of this is review highlights. So imagine if you search for some food, maybe you search for vegetarian-friendly Thai food, right? And then sometimes in the reviews, people would say things like vegetarian, veggie only, suitable for vegetarians. And then I'm sure there are way more synonyms for this. In the past, they had to get humans to write these different synonyms. And then they add this to dictionaries. And you can imagine this is not scalable. But now they can use LLMs to replicate the human reasoning, right, in the phrase extraction. And they get way better coverage and they can cover 95% of traffic. So for query segmentation, they are able to understand the user intent a little bit better. And then for review highlights, because they were showing more reviews, especially for the long tail queries, it makes search more engaging. By highlighting the relevant reviews for a user's query, they help the user feel more confident about the food. Let's say it's search vegetarian friendly, and then maybe the user review would really say something like, oh, the vegetarian food is great and delicious or something, or like definitely no meat involved. It happens to be gluten-free as well. I don't know. Things like that help make the users more confident in the search results that they're seeing. Okay, I'll pause here. Any questions? I know there's a lot in the chat. Oh my goodness.
There's a quick, I have a quick question on just this query understanding thing. What was the previous SOTA in query segmentation? Like, this seems like the most obvious dumb possible thing to do.
Name entity extraction.
Right?
You get a span, and then you train some kind of transformer model that takes the input, and then cut it at characters. Yeah.
Okay, so it's basically, but like this guy did not compare to NER, right? Like,
they mentioned that their original was NER, and this is better.
Okay, nice.
Yeah, they definitely. Yep. I mean, everyone starts with some kind of NER based approach.
My theory is that I basically there's no point doing traditional NER anymore. You just do LLMs with some kind of schema.
Could be.
NER fast.
Yeah, NER fast, NER cheap. That's it for search, right?
Gemini is free. Sorry,
free but slow. Free but slow, right?
Yeah.
Like if you want a spell check autocomplete thing, like a grammar tool, Gemini is slow.
So this is why I might rather prefer present from this. Where is it? Search query. So they started their legacy models. Their legacy models had several subclass. Yeah. So you can see name entity recognition, right? They use name entity recognition and they do this. But then, oh wow, people are drawing on this. I didn't know you could do that. But then they actually shared one thing I really like about this write-up is this chart right here. No, this chart seems very, very, very basic, right? Formulation, scope task, proof of concept, scaling up. But they wrote it very well to explain how they did it in the context of these two case studies. I feel like a lot of people just completely dropped this. They completely ignored this. And for query segmentation, right? I know I'm taking a long time to get to the point, is that 10% of queries make up 80% of traffic. So they could do all this query segmentation once, period, cache it, and then just retrieve from the cache. Derive golden data set, fine tune. I can't remember where they wrote it, but that's how they did for query segmentation and for review highlights. So essentially, a lot of these things that may feel like they have to be done online, but because of the power law in e-commerce and online search, you don't have to. You can make use of a cache a lot. There's also another question from Tyler Cross. How do these approaches compare to more information retrieval methods like BM25 vector methods? Tyler, do you want to? What do you mean by these approaches? What approaches specifically? Oh no, maybe Tyler's not on the.
I think he said this when you were doing the LLM, like we tried 3.5, fine-tune 3.5, llama 2, 7B.
Okay. I think that's like a classification. I think in this case, if it's a classification approach, then this wouldn't work, right? But if you're talking more generally, like using LLMs or embeddings for retrieval, yeah, I actually don't know. I don't know the full context of the question, so I probably better not answer. Okay. Any other questions?
Yeah,
Okay,
I think you hit on it. Yeah,
That's great. I can move on because the other two sections are fairly heavy, and then we have more time after that. Oh wait, I don't know if I'm sharing the right screen. Give me a second. Okay, first I need to go to my Google Chrome. See, this is what happens when you get a noob to do slides. Okay, share. You are seeing this, right? You're seeing my slides. Are you seeing it in slideshow mode?
Yes, full screen.
Okay,
slides.
perfect. So then the other thing is, I think there's some LLM inspired training paradigms. So maybe it's just LLM inspired, maybe you've been doing it for a very long time, but I thought to highlight it. The first one is really looking into scaling laws. And ever since I shared about this post, like people have gotten back to me with like at least 3 or 4 papers about other studies of scaling laws, but along a very similar view. So I want to talk about the experimentation that they did. This scaling law was decoder-only transformer architecture, and they tried various model sizes. The training data is the same as sentences, essentially fixed length sequences, 50 item IDs each. And the training objective is, given the past 10 items, predict item number 11. Given the past 20 items, predict item number 25. So it's fairly straightforward. But they did introduce 2 key things that are very interesting. The first one is layer-wise adaptive dropout. So you can imagine, right, for LLMs, every single layer has same dimension. Usually when they draw a transformer layer, it's every single layer has same dimension. But for recommendation system models, that's not the case. It's usually fairly fat at the bottom and gets skinnier towards the top. So what they do over here is they have higher dropout in the lower layers and lower dropout in the higher layers. And ablation studies showed that this worked. So the intuition here is that the lower layers process more direct input from the data. And because e-commerce data or recommendation data is fairly noisy, it's more prone to overfitting. Therefore, they have more dropout in the lower layers. Vice versa, at the upper layers, it learns from more abstract data, and therefore you want to make sure it doesn't underfit. You want to make sure it gets all the juice it can get, and therefore they reduce the lower, they have lower dropout at the higher layers. The other thing, which feels a little bit like black magic, is that they switch optimizers halfway during training. Firstly, they start with Adam and then they switch to SGD. The observation they had was that they ran a full run with Adam, ran a full run with SGD, is that Adam is able to very quickly reduce the loss at the start, but then it like slowly tapers off, whereas SGD is slower at the start but achieves better conversions. So they had to do these 2 tricks for their sequential models. What were the results? I mean, obviously, no, this is fairly obvious. Higher model capacity, reduce cross-entropy loss. And this model capacity is model params excluding ID embeddings. So it's purely just the layers itself without the ID embeddings. And they were able to model this. If you look at the dashed line, the test loss curve, and the blue dots, they estimated this with the blue dots, estimated that power law curve, and they were able to fairly accurately predict where the red dots are going to be. And this is like the Kaplan style scaling laws and the Chinchilla style scaling laws. Essentially, given such model, if we had bigger model, how would it perform? The other thing was, oh gosh, this lines don't look correct. Okay, the red arrow doesn't look correct. Everything else is fine. So over here, this is really, I think this is a very nice result, which is that smaller models need more data to achieve comparable performance. So over here on the left, you can see that there's a small model there on the orange line. It needed twice the amount of data compared to a bigger model to get similar performance, right? So the flip side of it is that, hey, if you want highly performant models online, you're going to need a factor more data. Of course, this is also nothing unusual. This is something we know, but it's really nice to have someone have done the experiments and distill it into the results here. The other thing that I thought was really interesting is this idea of recommendation model pre-training. So this was fairly new to me. I didn't think it could be done. Most people do this on content embeddings, which is given some content of this item, can you predict the content of the other item? I thought this was fairly novel, whereby it's trained solely on item popularity statistics. They say it works. It's still quite unfathomable to me on how it works. Essentially, just take the item popularity statistic, in the monthly and the weekly time scale, convert it to percentiles, and then convert those percentiles to vector representations. And that's it. That's your representation of the item. So anytime you have a new item, so long as you have the past statistic for the past month and week, you can convert it to percentile and then map it into vector representation. So what this means is that imagine if our percentiles are only at the hundreds and we have stats for monthly and weekly, all we need is 200 embeddings for a month and a week, and for each hundredth, for 100, and we need 100 percentiles, we need vector representations. So instead of millions of item IDs or billions of item IDs, all you need is 200 percentile vector representations. So that is extremely compressed. They also had to do several tricks like relative time intervals and fixed position encoding that don't come across as very intuitive to me. They explain that. They say that they did that, but it's unclear like how would I know a priori that I need to, how would I know if without running experiment that I needed to do it? So it feels like there's like too many tricks. There's so many tricks in like, okay, I need these three things, the stars to perfectly align for this to work. So I think it's very promising, but I wish there was a simpler way to do this. The results, it has promising zero-shot performance. What I mean by zero-shot performance, basically it trains on a standard domain and then tries to apply it to cross-domain, to another domain, right? And you can see 2 to 6% drop in recall at 10. This is compared to baselines, which are fairly good baselines, SASREC and BERT4REC, which are trained on the target domain itself. Now, if you take this model and you train it on that target domain, it matches or surpasses SASREC and BERT4REC when trained from scratch. But the test, it only uses 1 to 5% of parameters because it doesn't have item embeddings, right? It only has those 200 embeddings at the monthly and the weekly scale for every percentile. So this is quite promising in the sense it's one direction towards pre-trained models. You can imagine some kind of recommendation as a service adopting this idea, and maybe it could work. Maybe something like Shopify, right? Shopify has a lot of new merchants onboarding. Hey, can we take existing merchant data with their permission, of course, completely anonymized, right? It's just solely trained on popularity, right? And then we just train this model. Now for any new merchant that's onboarding, as long as we have a week of data, we can use the weekly popularity embeddings. And once we have a month of data, we can use that model. So we don't actually need semantic IDs. The second one is discussion, and we have two papers from YouTube. We have two papers from Google and YouTube here. And this is, so the one thing about distillation is that if you solely learn on the teacher labels, it is very noisy, right? The teacher models are not the perfect models. It's better to learn from the ground truth. But we do know that adding the teacher models does help. So what they do here is on the left side, you can see that direct distillation, which is learning from both the hard labels, which is the ground truth, and the distillation labels, which is what the teacher provides, the teacher model, the big teacher model provides, is not as good as auxiliary distillation. And essentially what auxiliary distillation means is that you just split, give them two logits, one logit to learn from the hard label, one logit to learn from the distillation label. And they find that this works very well. I didn't have time to put the results here, but they find that this works well for YouTube. And then the thing is the teacher model is useful. So what they did is that they amortized the cost by having a big fat teacher model. And by big fat teacher model, I mean it's only 2 to 4x bigger. By having a teacher model that's 2 to 4x bigger, this teacher model will just keep pumping out the soft labels that all the students can learn from. And this makes all the students better. And of course, why do we want students? Like if you're saying that teacher model is better, why do we want the students? We want the students because the student models are small and cheap. And at YouTube scale, where they have to make a lot of requests, this is probably what they need to do. Another approach, which is from Google, and I think they applied this in the YouTube setting as well, is called self-auxiliary distillation. So the intuition here is this. Don't look at the image first. So the intuition here is this. They want to prioritize high quality labels and improve the resolution of low quality. What does it mean to improve the resolution of lower quality labels? Essentially what they're saying is that if something is impressed but not clicked, we should not treat that as a label of 0. Instead, what we should do is to try to get the teacher to predict what that label is to smoothen it out. So if we look at the image, you can see that they have ground truth labels, which is those in green, and they have teacher predictions, which is those in yellow. So to combine the hard label with the soft label, they suggested a very simple function in the, I don't know if that's what they actually use, but essentially the max of the teacher and the student. So the max of the teacher and the ground truth. So imagine if the actual label was 0 and the teacher said that, you know, it's a 0.3, you just use the 0.3. Or if the actual label is 1 and the teacher says 0.5, you just take the 1. So by smoothing it and then having the student learn on the auxiliary head, right, you are actually able to improve the teacher model itself and use it for serving. So there's a lot of distillation techniques, which I think is quite inspired by what we see from computer vision and language models. I haven't seen too many of these distillation techniques myself in the field of recommendations, which I thought were pretty interesting. The last one, and unfortunately this is the last one I have slides for. I can go through the other recommended reads I have, but unfortunately I didn't have slides to do for it. Is this one. So this is quite eye-opening for me. Essentially, what LinkedIn did was they replaced several ID-based ranking models into a single 150B decoder-only model. What this means is that, for example, you could replace 30 different logistic regressions or decision trees or neural networks with a single text-based decoder-only model. This model is built on the Mistral MOE, right? That's why it's like approximately 150B. And it's trained on 3 to 6 months of interaction data. And the main, so you may think, okay, decoder only model, what does it mean? Will you write posts for me? Will you write LinkedIn posts for me? Will you update my job title, whatever? The focus here is solely binary classification if the user will like or interact with a post or apply for a job. So you can imagine that this model probably only needs to output like or not like. It's probably more complex than that, but essentially this is a big fat decoder model that is very good at binary classification. That's why it's able to actually do well. And that's how they were able to evaluate it. So there are different training stages. And over here, I think maybe it's better for me to go into the actual write-up itself, because I just didn't have time to show this. So they have continuous pre-training. So continuous pre-training, they just take member interactions on LinkedIn, different LinkedIn products, right? And then raw entity data, essentially just take all this job hunting related data to pre-train the model to help the model get some idea of what is the domain. After continuous pre-training, they do the post-training approach, they do instruction tuning. So essentially this is like training the model, follow instructions. They use UltraChat and internally generated instruction following data, right? So get LLMs to come up with questions and answers relevant LinkedIn tasks, and then try to find high quality ones. So that's training it, fine tuning it to follow instructions. And then finally, supervised fine tuning. I know they say a lot of things like multi-turn chat format, but essentially the goal for supervised fine tuning is to train the model to do the specific task. I don't remember where it is exactly, but it's like so this is a specific task. So now that we know it can follow instructions, now let's make it better at the specific task. What action would a member take on this post? Would it solely be impressed? Will it be liked? Will it be comment, etc.? So that's how they go through different steps. And I'm going back to my slides. Okay. So they have these 3 different stages. And so here's the crazy thing. You can see the slides, right? Can someone just say yes?
Yes. Slide.
Yes.
Yes.
Okay. The crazy thing is that they have now replaced feature engineering with prompt engineering because of this unified decoder model. So you can broadly read it. It's like, this is the instruction. Here's the current member profile, software engineer at Google. Here's their job. Here's their resume. Here's the things that they have applied to. So will the user apply to this job? And the answer is apply. And you can probably simplify this into a 1 or 0, right? I guess they just say in text as an example, but That's all this model is doing. For a user, we have retrieved several jobs. This model is doing the final pass of which one to rank. And they take the log props of the output to score it. So essentially, if this says that the member will apply, maybe we have 10 jobs that a member will apply, then we take the log props to rank it. I don't know if this is a good thing or a bad thing. I find feature engineering more intuitive than prompt engineering, but maybe it's a skill issue. But essentially now all PMs can engineer their own features. The impressive thing is that this can support 30 different ranking tasks. That's insane. So now instead of 30 different models, you just have one big fat decoder model. That sounds a bit crazy to me. Firstly, it's crazy impressive. Secondly, it's a lot of savings. Thirdly, I don't know how they deal with the alignment tags, or maybe it's just a do no harm tags. I don't know. Essentially, the goal of RecSys was to decouple everything, right? It's like have retrieval be very good at retrieval, have ranking be very good at ranking, and then each model just squeezes as much juice as we can. Now, what this is saying is that, okay, we're going to unify it. We have too many separate ranking models. We're going to unify into a big fat model and then push all the data through it, and hopefully you'll outperform. And it does outperform. It needs a lot of data. So you can see in the graph over there, right? Up to release 3, it was not better than production. And you can see that based on the axis on the left, which is the gap production. 0 means that it's on par with production. Up to release 3, it was not better. I mean, I don't know who had to get whatever budget or like just to quarterback to make sure that this worked, to push this through. But as they add more and more tokens, it's better than, it starts to get better than production, like 2.5% increase. So this is a huge leap of faith that, okay, we just say, bitter lesson. Just give us more data, we will outperform, and with a single model. Okay, so that's it. That's all I had to share. I can go through I want to just briefly highlight 2 other papers, which I think are good. It's a little bit less connected to LLMs, but the 2 other papers which I think are very good is because of how they go into their system architecture. The first one is Etsy. Etsy, you can see this is extremely complicated, but this really shows you a very realistic and practical approach, right? Classic 2-tower architecture, they share about negative sampling, and then talk about product quality, right? The thing is, you can have very clickbaity crap, realize images, but when people buy it, they return it. You'll never be able to detect that if you're just using that. So what they did was that they actually have a product quality embedding index that they use to augment their approximate nearest neighbor index, right? So you can see the quality vector. This is extremely pragmatic, and I can tell you that no e-commerce website or no search engine, whatever online discovery thing can do without some form of quality vector or some kind of post-quality filtering. We saw that with Indeed, right? Expected bad match, they needed quality. They just operationalize it in a different way as a final post-filtering layer. Over here, they include it in the approximate nearest neighbors index. So I highly recommend reading this. Very practical, shares a lot of detail into their system design. The next one I also highly recommend is the model ranking platform at Zalando. I think this is all the best practices, talks about all the different tenets like composability, scalability, steerable ranking, and they really go very deep into, hey, here's the candidate generator, essentially the retrieval step, 2-tower model, and then they just using an ANN to retrieve it, and then they talk about the ranker, and then finally the policy layer. What is this policy layer, right? Policy layer encourage exploration, business rules like previously purchased item diversity. Again, some measure of quality that the model will never be able to learn from the data. The model will never learn that showing good items is good, right? Because they're untested. So you have to override the model with this policy layer. And of course, very good results. But what I really like about this paper is that if you want to learn about system design for RecSys, like the Zalando paper and the Etsy paper are really, really, really good and really in-depth. But of course, everything here is very good. If there were a few papers I read, I'm like, okay, this is pretty crap. I wouldn't include it. But every paper here is pretty good for system design under the final section, which is unified architectures. Okay, I spoke a lot. Any questions? Did I lose anyone? Did I lose everyone?
Eugene, I have
Yes.
one quick question to double check on the LinkedIn's paper. My understanding is the big model on the 150 billion model is actually used as teacher model and then distill the knowledge into smaller models, then used for kind of different tasks. So I don't know if that aligns with your understanding, because practically 150 billion model and serve that for prediction, the latency will not be acceptable and too costly also. They do actually have a paper discuss more about how knowledge distillation is happening with that 150 billion models. I kind of put it in the chat. I don't know if you have come across that paper.
I have not. But my impression was that they were actually using it. Thank you for sharing this, and thank you for correcting my misunderstanding. I need to look deeper into the original paper to confirm this.
Let me tag you in this thread. That's my understanding. So, but I also find this the approach very interesting. So we're actually thinking of similar kind of approach and as well. But at least they kind of prove that this way kind of works. Yeah.
Thank you. I think that could probably be it. I think there's no way for it to be feasible to serve it at that scale. I think you're probably right. I don't know. I didn't see anything in the original paper that actually suggests that. But I think you're right. There's just no way for it to serve it at scale.
Yeah. So I checked you in that thread. Maybe I can.
I have the paper. Thank you. I added to my save list to confirm.
Okay. Yeah. Thanks for explaining this. Just to double check. Yeah.
Thank you. Any other questions?
I mean, so one thing that I try to look for and I found myself doing, but I might as well ask the pre-trained LLM that is you, is to rank what is highest, the lowest hanging fruit versus the higher ones. So for example, right, the way that you organize your write-up was 4 sections. It was model architecture, data generation, scaling laws, and then unified architectures. Why? There's no particular reason. There's no order, right? Like, to me, it was very clear that model architecture is basically useless. Is that true? Would you recommend?
I don't think so. I actually think that I think the model architecture right now is like a little bit more like innovator's dilemma. I would say that in 2023 it's useless. I haven't seen good results. Now I'm seeing good results.
Would you classify this YouTube one as a good result? Because I read it, I was like, wait, like this, I don't know, like these are smart ideas, and then the results are like, doesn't really outperform our baseline.
I think it's decent results. Coincidentally, after I published this, I think after it made the rounds on Hacker News, people from YouTube actually reached out. One of the authors on this exact paper actually reached out. They wanted me to like go in and chat with them. And then they're like, we have more papers, we're pushing to publish it. And this is a perennial problem, right? Especially for YouTube and TikTok, right? New videos get uploaded all the time. They have to deal with code. Cold start is their bread and butter. So I wouldn't be surprised that they are focusing so hard on content embeddings for cold start.
This is for a new video, but not, I mean, they have users, they have user histories, and basically they saturated the world on that.
I think very likely so, right? You can imagine YouTube, Twitter. I mean, it's unmentioned here, but ads, Google ads, it's always cold start. Being able to crack this cold start problem, just even 0.1% is huge. It is huge. And you can see a lot of the papers in this semantic IDs, YouTube, Kuaishou, which is like TikTok. Huawei, this one I'm not very sure why they did this. Yeah, a lot of it, CowRec. Also, solving CoStat. So yeah.
Okay, but like, orders of magnitude is which takes
Orders of magnitude, I really think that the lower hanging fruit right now is really using LLM data generation to
right?
help.
Yeah, that's my I mean,
To
obviously
me, that is the I think everyone can do this now. And the expected bad match paper Indeed did, right? I actually did this last year. Something very similar. I did this last year. It got published internally. This is very, 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 very effective. This approach of starting from somewhere, active learning, fine-tuning a model, more active learning, it really helps improve quality. I was doing it in the context of LLM and hallucinations, but you can imagine doing this in terms of relevance, in terms of any level of measure of quality that you want to focus on. It will work very well.
Okay.
And
So
then of course,
data
yeah,
generation, then architecture.
I would say data generation and then like model architecture and system architecture.
Yeah.
Oh wait, actually the even the scaling laws part, there are some things that are very practical. One example is, which I didn't have time to go through, is this basically LoRa's for recommendation. So what they did is they train a single model on all domain data. You can imagine all domain like fashion, e-commerce, fashion, furniture, toys, etc. Or it could be like all domain like ads, videos, e-commerce. And then after that, they have specific LoRa's for each domain. And this works very well. So I definitely think that essentially right now, it's not easy to learn from data across domains for recommendation system. It's actually for recommendation system, and correct me if I'm wrong. I really think that you want to overfit on your domain. You want to overfit and predict the next best thing for tomorrow. And that's it, period. I can overfit and just retrain every day. But yeah. I know we have a few questions here. Daniel, shouldn't the LinkedIn model combine with an information model that's used to generate? Yes, correct. There's probably an upstream retrieval model, and then the LinkedIn model just does the ranking. So in the two-step process, you have a retriever, the decoder model, I think just does the ranking. For LLM-based search retrieval, any papers talk about impact of query writing prompt engineering, also sensitivity. I think we know that LLMs are sensitive to prompts, but I think they're increasingly less sensitive to prompts because they're just way more instruction tuned. I'm not sure about LLM papers that talk about the impact of query writing. I think the only one that I have seen, at least covered here, is the one by Yelp. So I think that could be helpful. What's the process for keeping these hybrid models up to date and personalization? Keeping them up to date, that's a good question. I don't know if they actually need to be kept up to date. So if you look at these hybrid models, right? Let's just take this semantic ID embedding. It actually uses a frozen video bird. Similarly, for Kuaishou, they use frozen sentence bird, ResNet, and VGGH. So the content itself doesn't need to be up to date. And the assumption is that, okay, content today is going to be the same as content tomorrow, is going to be the same as content from 1 month. So that is not up to date. But what is learnable is the semantic ID embedding and the cluster embedding. Now, for personalization, that's very interesting. That's the hard question, right? And the personalization, I guess, how you include personalization is, okay, after we learn the content, we also need to learn what the user is interested in. And that's how they have this two-tower approach. And that's why you can see over here, there's this small layer, which is multimodal interest intensity, right? Which is given a user and their past historical sequence. How can we tell what layers are, what modality they're interested in? I think that's how they do personalization over here. Any other questions? If not, we can always ask for volunteers for next week's session. Anyone? Okay, suddenly everyone's so silent.
No, I think this is really helpful. It just feels like RecSys is always these bundles of ideas.
Yeah.
Like in the way that agents are bundles of ideas for LLMs, RecSys is also a bundle of ideas, and I think that they are obviously converging. You don't
Yeah.
really, yeah, I mean,
I definitely think so, right? And you can see examples, right? We learned item embeddings via word2vec. You know, when people talk about graph embeddings, essentially just taking the graph, doing a random walk, converting that random walk into a sentence of item IDs, and just using word2vec. Similarly, learning the next best action, GRUs, transformers, and BERT, very obvious it will work. So I think we will see more from the LLM space being adopted in RecSys as well.
what is the link in your mind between re-rankers and RecSys?
I think so. In RecSys, we have retrieval and recommendation, right? So you can see over here, where is it? So what we do over here is retrieval will retrieve a lot of top candidates. It's going to retrieve 100 candidates. And then ranking is going to find the best 5 candidates. You can focus on the best 5. I think it's the same thing in retrieval and re-ranking, in ranking and RecSys. What people say in reg as re-ranking, I think it's just really just taking retrieval and then finding the best 5. And, you know, Cohere has re-rankers and finding the best 5 for the LLM as part of the context.
Yeah, to me, it's a bit weird, right? Like the re-ranker models are being promoted as a way to just, you feed in your top K whatever results, and then they re-rank them, and somehow that is supposed to produce better RAG because the more relevant results is at the top. But without the context that RecSys have, for example, user preferences and user histories and whatever, like how can you have any useful re-ranking at all, right? Like
I think there are some ways. So for example, like maybe retrieval, right? You can imagine the most naive retrieval is really just BM25 or semantic search. Now, then you can imagine you have a lot of historical data on all these BM25 and his semantic search and all the associated metadata, which you probably cannot use in retrieval stage because it's too expensive. And then you can just train a re-ranker. You just say that when the author match, or this author usually looks for this kind of document, and then you can try to re-rank it. I think it's possible. I haven't dove too deep into how re-ranking is done for RAG, but it's possible. Oh, Opulensha, you had a hand raise.
Yeah, no, thank you so much, Swix and Eugene. Yeah, you guys are amazing. I'm huge fans of you both. But the question I had, I guess, is it worthwhile for an organization to go and build this when you have something like Gina.ai, who, as we know, popularized a lot of work on deep search and not just internal retrieval, but external search and retrieval, because they have the embedding models, the re-rankers, the retrieving deep search APIs, all unified. How do you feel about that, Eugene and Swix?
Should teams build it themselves, or should they just buy something off the shelf?
Yeah, like Gina.ai has kind of this full stack that you're talking about with all these fine-tuned clip models, embedding models, re-rankers. They have the deep search retrieval. They've posted probably some of the better technical blogs on deep search. I think that's out right now, and embedding models and re-rank.
Yeah, my answer is going to be probably very boring, and you can apply it to any answer, whether someone should use an LLM API off the shelf or just fine-tune a model. I think that for prototyping, just do whatever is fast, right? Demonstrate user value. It's going to get to a point in time where what you need does not fit what something off the shelf is going to do. And that's what that's Indeed's story, right? For expected bad match. Latency continue to be too high, even if they fine-tune it through GPT-3.5, latency continue to be too high. The only way was to fine-tune their own model. Similarly, like for retrieval, you can imagine, okay, they're going to provide a lot of out-of-the-box embeddings, and maybe it's going to be good enough. And then finally, you want to really squeeze more juice out. You probably need to go fine-tune your own embeddings. I know like Replit recently shared something about fine-tuning their own embeddings, half the size, etc., and it does way better. There are a lot of examples here. I think Etsy also fine-tune their own embeddings, and it outperform embeddings out of the box. I think it's a little bit of unfair comparison. I think if you take those models, those embedding models, and you further fine-tune them, I think they could do better. But essentially, the point by just use what's off the shelf to move fast, and then after that, if you do need to customize it, then you customize it.
I love it. Thank you so much. Super helpful.
You're welcome.
Hi, this is Wei. Sorry, we have a question.
Go ahead. And I think this is probably my last question.
Okay. What do you think of the biggest opportunity in terms of for apply LLM in recommendation domain? Because we discussing retrieval, ranking, content understanding, etc. Right? There are so many different prediction tasks.
You're asking me what I think is the big opportunity? Is that your question?
Yeah.
I think embeddings, I think what we've seen is that embeddings are helpful for retrieval. So instead of purely keyword retrieval like ant killer, someone might just ask ChatGPT, I have ants in my house. I think a semantic embedding could be able to help you match that. And I think ranking is definitely clearly, it will clearly work. Using an LLM based ranker, I think LinkedIn can clearly work. And of course for search, I think there's this guy Doc Turnbull. He's increasingly going down the route of, and we've seen examples from Yelp, right? Using an LLM to do query segmentation, query expansion, query rewriting. It clearly works in Yelp's use case, and you can just cache all of these results. So those are the three things I off the top of my head that I can think of. Okay, thank you everyone. I do need to drop. Maybe you can discuss what the next paper is. Maybe Six will talk about Moore's law for AI and every 7 months, which I think is interesting.
No, now the image generation, autoregressive image generation is the hot.
Okay.
All right, bye. Thank you.
Thank you, everyone. Take care. Bye.
Thank you.